Yeah, let's welcome back. Yeah, today I'm going to continue the Turss equation. Then we already learned about the direct stiffness method and potential minimum approach method. So that today I'm going to introduce one more method to derive the stiffness equation. Yeah, especially Galeckian method. So then today I'm going to show you the FEM two-dimensional truss code by MATLAB. So we can compare our numerical analytical solution with the console software. So let's continue. Yeah, today our running object is we are going to learn about Galeckian residual method, which is a new way to derive the stiffness matrix or equation for the bar element. Yeah, after the running, yeah, similarly energy minimum potential approach method, yeah, we can derive the partial difference equation of FEM equation from the partial difference equation. So after the running Galeckian residual method, I think you can derive the all kinds of partial difference equation into the FEM formulations. So yeah, but in the textbook, yeah, both method, energy minimum approach method and Galeckian residual method introduced in our main textbook. So yeah, in my opinion, Galeckian residual method more straightforward to derive the FEM equation. However, the concept is slightly confusing compared to the energy approach method. It is because that energy approach method is if you understanding the term of the energy for our systems, you can easily define the energy equation. Yeah, sometimes that it is confusing that defining energy, but if you can easily define the energy term of your system, so you can derive it easily using the variational approach method. However, yeah, compared to the energy method, the Galeckian method uses a partial difference equation itself. So yeah, you don't need to handle some equation into the other term, for example energy term. So you can directly use a partial difference equation. However, some concepts of the residual is slightly confusing when you're first learning, but today I'm trying to understanding what is the residual method in the partial difference equation. So let's follow the step by step. And then, yeah, I think that last lecture I skipped some symmetric structure. So our FEM structure more become complex, yeah, in the two-dimensional spaces. So yeah, so when you define your system, we have a lot of elements. That means that we have much or many degree of freedom in the system. So yeah, that makes large size of the local or global stiffness matrices that require a lot of computational cost to obtain the solution. Yeah, so yeah, to reduce the computational cost, I mean that reduce the stiffness matrix size, so that we have one technique. First technique is a symmetrics. Actually, we have several types of the symmetric characteristics. Yeah, reflective symmetrics or mirror symmetrics. That means that if you have some structure, for example, you have half circle cases. If you want to simulate this one, so that you can use only a half circle. It is because the left one, the other one shows the same behavior. So that at that time you can reduce your system looks like this way, so that maybe the mirror and reflective is a very, there are some reflective symmetric characteristics, and then or other axial symmetric cases means that if we have some circle, we have some result into the radial direction. At that time, you don't need to worry about the angular derivative. We can only handle some variable in the radial direction. That means that we can reduce the dimension or shapes of our system. So at that cases, so we can reduce our degree of freedom of the size of the system. So however, those kind of reflective symmetric cases, so we do not handle it is because that if you want to handle those kind of symmetric cases, we should changing our equation in the Cartesian coordination to some cylindrical or spherical coordination system. So I like those kind of coordination system. However, it will make some confusing or make harder to study to understanding the concepts of the symmetric characteristics. So today I'm demonstrated only reflective or mirror cases. So reflective symmetric means that if you I think that to explain the compared to the explaining the meaning of the reflective symmetrics, I think that it's more easier to understanding to show some real cases. I prepared some example problem in our textbook. So here the example. This structure consists of the truss, 1D truss element in the two-dimensional spaces. So we have 1, 2, 3, 4, 5, 6, 7, 8, total 8 elements in this system. And then how many nodes exist in here? It's very important. 1, 2, 3, 4, 5. So that we have a total 5 nodes in this system. So in this system, we can expect the global stiffness equation. I mean the size of the global stiffness equation. Can you guess? So we have 5 nodes point, 5 nodes, and then each node has a 2 degree of freedom. First degree of freedom is in x direction. Second is y directions. So first node has a displacement in x direction. Second degree of freedom is y displacement. So if you use a u and v variable, you don't need to the subscription x and y. This is for the first node. Second is looks like this. Similarly, maybe last one it looks like this. Total we have total 10 by 1 vector for the displacement. So similarly, first vector will be have f1x, f1y, f5x, f5y. So that also that will be 10 by 1 vectors. So that means that our global stiffness matrix maybe must be the 10 by 10. So it's very huge matrix, but you can easily solve the solution by some computational software. But by your hand, yeah, it takes a lot of time to assemble first. Yeah, it takes a lot of time to assemble the local stiffness matrix into the global stiffness matrices, and then after applying some boundary condition, yeah, so we can maybe we can obtain the reduced stiffness equation. So but we don't check yet about the boundary condition detail. So so anyway, we should take inversion 10 by 10 matrices. Yeah, I don't think you can do, yeah, you can take inversion of the 10 by 10 matrices, so that it's very hard, it's very difficult. Yeah, so yeah, to make more simpler, we can use our symmetric characteristics. Yeah, in here, although we have 8 element, 5 nodes in this 2D truss system, but we can easily expect some deformation. Yeah, you can expect the deformation of this structure. So yeah, we applied force at first node and in y directions. Yeah, there are no axis forces in x direction. That means that this structure will be deformed only in the y direction. Especially, yeah, this point already fixed. Yeah, the result will be equal to 0. Yeah, and then remaining nodes, yeah, due to this y-axis force, so that this node will be deformed in y directions only. Yeah, so due to those kind of cases or boundary condition, yeah, let's think about this solid this system, this reduced system. Yeah, this second nodes are fixed, and then first node fixed, and second and third and fourth node have some roller boundary condition. Roller boundary condition means that this node can move in the y direction only. Yeah, yeah, there are no displacement in x direction. So anyway, so yeah, these 3 nodes has a roller boundary condition and then forces, and looks like this. Yeah, yeah, forces are reduced. It is because that we cut this 2D system, so that this truss, yeah, or if this truss has a cross section A, 2A, yeah, 2A, yeah, will be, yeah, we also we obtain the half size of the cross section area of the truss element. So that, and then, yeah, also forces become half. Yeah, due to this external force, the second and third and fourth node will be deformed the y direction only, and then that result we can easily expect it exactly same. So yeah, and then yeah, here we have 1, 2, 3, 4, 5 element, and 4 node. That means that, yeah, our global size of the global stiffness matrix is expected. Yeah, although each node has a 2 nodal degree of freedom in here, so maybe the 8 by 8. Yeah, actually, yeah, there are no benefit use a symmetric structure. It is because that, yeah, compared to their origin size of the global stiffness matrices, yeah, 8 by 8 is very similar. However, in here, this 3 node has only single degree of freedom in here, so we can easily expect it, maybe this, yeah, if we neglected the displacement in the y direction, axis direction, yeah, total global stiffness matrix size is equal to the 5 and 5. So yeah, at that time, and in these stages, compared to their 10 by 10 global stiffness matrix, this will be have a large benefit to obtain the solution. So this is why we use a symmetric characteristics. Okay, let's try to this example first. So do you remember the result of the local stiffness matrices in the two-dimensional spaces? In the one-dimensional cases, the AE over L, 1 minus 1 minus 1 and 1. This is a result. However, in the two-dimensional cases, we will use expanded matrices. 1. And then this local stiffness matrices will be rotated, so that this rotation can be done by, how can you do that? Using the transformation matrices. So maybe F equal KU. So in here, we use a rotational transformation matrices in here. Maybe it looks like this. And then finally, maybe inversion is equal to the symmetric transpose matrices of the transformation matrices. That result is looks like this. To solve it, please memorize this equation, or how to derive this equation. So anyway, here let's start. First element, let's check the first element. First element has a cross-section area and Young's modulus, and then if we put the length of the L, and this also equal to L, that means that the length is a root L. And then this first element rotated the 45 degrees in the positive direction. That means that theta is equal to the 45. To obtain this result, first solve with the cosine and sine theta, or cosine square and sine square. So in here, so you can put their size is equal to the root over L, and then cross-section area is equal to, I think that, if I skip, I didn't check the details about the cross-section area, so that I think that this is the first, although I do not mention about the cross-section area, that cross-section area is equal to looks like this, maybe. Please check the details. So that, and then here cosine square is 1/2, and then multiplication cosine and sine theta is equal to the also positive half, and then 0.5, and then this part minus 0.5, and then this is also minus 0.5. After make first local stiffness equation, and then second, let's check the second one. Second one is has a minus 45 degrees rotations, so or 350 degrees. That result, the sine value have a positive value, so that the matrices looks like this. And then third node, there are no rotations in here. So, and then cosine and sine value are equal to the 1 and 0 with respectively the result. In here, cross-section area is also A and length is L. And then first element in here, cross-section area can maybe half its origin. Actually this element has a 2A cross-section area. However, due to the symmetric cutting, so that the surface's cross-section area is equal to A. So that, and then here Yeah, first, this is a first element, this is a second element, and this is a rotated 45. And then in here, what is the first and final, I mean the initial and final element? I think many guys think that this is a correct cases. So yeah, rotated position looks like this. That means that minus 40, or sometime, yeah, depending on your favor. So yeah, I'm not sure that which one is correct, but in my opinion, yeah, this maybe looks like this, in my opinion. Yeah, maybe. So and then yeah, and 3 and 4, yeah, this is a basic cases, and then this is a basic cases. That means that this is a, yeah, this is a positive rotation, positive direction rotation about 19 degrees. But in my opinion, yeah, it's correct maybe. But yeah, this manual textbook shows this result. So that although next time I'm going to use those kind of equations, but yeah, just use it. Yeah. So and then anyway, the transformed local stiffness matrices looks like this. And finally, we obtain the total 5 local stiffness matrices, and then we should assemble these equations, these 5 local elements into the, yeah, how can you obtain maybe the, yeah, we have a 4 nodes, and that means that 8 by 8 matrices. And then in previous slide, yeah, maybe this is for the first element. Yeah, maybe this result, this part looks like this. Yeah, however, yeah, second element is affected by the first element in here. Yeah, they use those kind of notation. So if when we use minus degree cases, yeah, I think that we can put this value and looks like this. At the time, yeah, this 0 and 0 and this 0 and minus 2 1분의 1 1 over 0.5. Yeah. So yeah, that's why I use same angles in here. So anyway, yeah, sorry, I do not, yeah, here, yeah, this is a first node point. Yeah, maybe U1 and V1, and then this is yeah, this is for the second node point. Oh, sorry, not second node point. This is a second node element, so I think that we should added this part equal to 0 and 1 over 2, or I mean that I want to add this value in here. Yeah, looks like this. However, I forgot the factor, coefficient, whole value are same, so you don't worry about the coefficient. Yes. So anyway, looks those kind of way you can add the whole 8 by 8 matrices in this global stiffness matrices in here. So and then your displacement vector and looks like this. Yeah, we don't need to talk about. Yeah. So anyway, so and then yeah, we finally obtain those kind of equation. Yeah, for your convenience, I'm going to also write down. Yeah, in here. So let's apply our boundary condition in here. Yeah, first element, first node has a fixed is fixed. That means that this becomes 0. We have a 2 0 in here. And then second and third and fourth node are Euler boundary condition. That means that there are no displacement in x direction. That means that this value equal to 0. This value also 0, and all u values equal to 0. And then let's check. It's all done. For the displacement. Let's check about the forces vector. First element, that will be have some reaction force in x and y direction both, and then here some reaction. We can expected some reaction value in here, but due to the some but continue this part. Also anyway. However, fourth node, so that they applied some external force in the p with minus directions. So anyway, and then I think that this part equal to 0, and then there are no forces in the second and third node point. However, there we can expected some reaction force in here. However, this unknown value in force vector, so that we can obtain after the obtained solution displacement first. So then we have a 3 unknown variable in here. That means that v2, v3, v4, and then their external force is equal to 0, and minus p. And then in the 8 by 8 global stiffness matrices, we can reduce the whole vectors, but maybe we can obtain these 3 columns in here. But similar manner, we can cancel out some value, and then finally, we obtain those kind of value in here. This is some reduced cases, and then this matrix is a 3 by 3, so that you can solve this. You can take inversion of this 3 by 3 matrices, so that you can finally obtain this value in here. So it's very easy. So, and then after obtain the solution, you can insert this value in here. Finally, you can, after multiplication, we can obtain the reaction forces in this system. So it's a very it's a simple cases of the symmetric system. So although symmetric technique can reduce the size of some system. However, so 2D cases has actually already have a lot of many degree of freedom. So finally we obtain the very large size of the global stiffness matrices. So so it takes a lot of time to obtain the solution. So actually, if the computer can help you, so you don't need to use a symmetric techniques. Actually, actually 10 by 10 cases, very small degree of freedom. But let's think about some 3D solid structure, and then each node has at least 3, or depending on your system, 6 degree of freedom. And then you discretize using a lot of element. So we have millions of the degree of freedom at the cases. Although MATLAB is powerful to handle some matrices, but it takes at least a few hours to obtain the some solution or inversion matrices of the millions size of the matrices. So at that time, if you applied those kind of symmetric technique in your FEM model. Yeah, you can reduce at least half, and also maybe size will be expanded at least number of elements. Yeah, first, yeah, 1D cases that will increase the and power rows. Yeah, however, in the two-dimensional cases, there will, yeah, maybe, sorry, yeah, maybe, yeah, sorry, yeah, looks like this. Yeah, maybe, yeah, first 1D cases that will increase the linearly. However, in the 2D cases, yeah, their size will be increased the power seconds, power rows, and then in the 3D-dimensional cases, yeah, increase the dramatically more than 2D and 1D cases. So that, yeah, anyway, so yeah, these techniques, yeah, actually in the previous few decades ago, yeah, computer does not show a good performance than state of art technology in these days. So it takes a lot of time to obtain the solution. But these days, yeah, you don't need to worry about it. Yeah, in the 1D or 2D cases, yeah, our computer has a very powerful performance than decades ago. So, however, yeah, when you solve this FEM problem by your hand, yeah, these symmetric characteristics will be very powerful to obtain the solution. So please remember, and then, yeah, practice. If your system is too large to handle by your hand, yeah, please apply those kind of symmetric characteristics. Actually, I introduced only one simple cases, only reflective cases, but in our textbook we have some many practical problem about the reflective cases. So anyway, yeah, let's continue the next topic. Yeah, in this slide we are going to learn about another way to derive the local stiffness equation for the FEM method. Yeah, first, yeah, is a weight residual method. Actually, this method is can apply directly to the difference equation, ordinary or partial difference equation, to make FEM equations. Yeah, in this method, yeah, so we have some approximated, so, or we can use, we are going to use some our slightly virtual variable, independent variable. So at the cases, so anyway, yeah, meaning of the residual. Yeah, residual means that actually some error. There are some error. Our partial different equation. Yeah, if we, yeah, in solid mechanics we have those kind of equation. Actually, yeah, so we already told you about those kind of relationship. Yeah, from the Hooke's relationship. Yeah, maybe, yeah, the strain. Yeah, if we have a constant Young's modulus and the value and looks like this. Yeah, finally we, yeah, obtained some Laplacian equation when you neglected the body system. So yeah, those kind of difference equation. Yeah, our numerical solution. Yeah, computer, actually we cannot obtain the exact solution by numerical method. The solution maybe will have some error, computational error, or sometimes models error. However, in this today, yeah, maybe computational, some numerical error. So some, and then, yeah, if we applied exact solution, the equation become always equal to 0. However, our numerical solution, yeah, maybe slightly give some error, so that does not equal to actually exactly not 0. However, we can say that approximately 0. So that means that, yeah, our purpose, what is our purpose? Yeah, our purpose is yeah, become 0. Yeah, this is residual. Yeah, so our purpose is we want to minimize this residual error by our numerical solution, so this weight residual method is a technique to reduce the error, not strongly related to the FEM method. Yeah, this method is not related to the FEM itself. Yeah, this weight residual method technique to reduce some numerical error. So yeah, so I already show you that what is the error. Yeah, if we have some exact value, sometime we obtained some numerical error, numerical value that will have some residual exactly error. So our purpose is to reduce this error, so that today we are going to show how to define error or how to reduce this error. Depending on your system, we are going to use various types, different types of the residual. We are going to define some residual, and then in here. So in the galactic residual, actually this residual error, maybe they have some domain value in your volume integration. Actually let's think about we have some numerical displacement value in your exact value. It looks like this. However, numerical solution and looks like this. There are some this is some error. So anyway, so depending on your discretized system, we are going to check the error in the whole domain, so that we are going to integrate this error. After the error, maybe we strongly hope that this summation of the error is equal to 0. That means that we can easily say that this is numerical or approximated solution exactly same to the exact solution. So it's very happy. However, it is hard to obtain the exact solution by our numerical technique. So so we slightly added some virtual value in here. So summation of the error, it is hard to become the 0. This residual cannot become 0 actually, but this arbitrary value will assist this summation of the multiplication error, and this arbitrary value is equal to 0. So sometime some reason the error does not 0. However, at that time this arbitrary value will become 0. So that we are going to use some arbitrary value, so that we can make those kind of very mathematically some very good cases. So anyway, so the total integration, we can say that equal to 0. So compared to the simple summation of the residual error equal to 0, compared to this one, this one maybe we can easily obtain some numerical solution than this one. It is because that these cases have only special cases match this condition, but due to the additional value, we have more opportunity to obtain those match this relationship. So at that time, yeah, this w is a weighting functions or weighting variable. So this weighting variable is a arbitrary value. Arbitrary means that, yeah, we can use any function, any values. So that, yeah, due to this weighting function, so first time it is hard to understanding the meaning of the weighting actually, but it's just arbitrary value. So in mathematically, actually, it has some meaning, but this is our purpose, so that I'm going to skip the detail. So anyway, yeah. So due to the how to select a residual and then how to select that weighting function, we have several types of the method, collocation method or subdomain method or least square method, or finally, Galerkin residual method. Collocation method means that we are going to directly use a summation of this residual error whole domain is equal to 0. So that's the first way to obtain those kind of things. Least square method. Least square. Square means that we apply some square value in residual error, and then after that will be equal to 0. So actually sometimes some variable shows a positive error and negative error depending on your system. However, total summation equal to 0. However, there are this is an error. Although the summation of the error equal to 0 means that there are no error in this system. It's a wrong answer. So so that we have several way to changing this error. So that first, actually we have those kind of technique to changing take absolute values of the error. However, for the convenient to handle by mathematically, so that we normally apply the square or sometimes norm2 error. So anyway, so and then Galerkin residual method is I already we seen in the previous slide. This equal to 0. So that Galerkin method more powerful than compared to this 3 one. So that I'm going to introduce only Galerkin method only. So let's try into the details. Although we do not understanding the weight function, but let's start. We have those kind of partial difference equation. L is just some operator of the derivative. We are going to handle the only one-dimensional cases. This L may be equal to the ordinary difference operator. And then P is an exact value. So for example, our equal to, we normally put this P equal to 0, but if we have this difference equation where we have some values in here right hand side, you can use it. But in equilibrium equation, P is always equal to 0, so that you don't need to worry about it. So anyway, so to match these two equations, the L operator looks like this. This U equal to P, P equal to 0, and then U here, and then remaining thing is become operator. In here, that become some Laplacian operator in here. So anyway, if you please do not confusing. This is an exact solution. This is a numerical solution. If we obtain the exact solution after taking this operator, we are going to obtain this phi value exactly. However, if we have some we have some numerical solution which containing some error. At that time, yeah, this is just slightly different. Yeah, it is hard to say that this exactly become P. So, and here, so our head means that this is a numerical solution. So this numerical solution, maybe we can use it to see it. Yeah, so exactly, yeah, this is a exact solution. So that will have some residual error. Yeah, due to our intrinsic problem. Yeah, numerical solution always has some error. It is because that we only solved and obtained the exact solution at only nodal point. We have some approximation in the inside element. So the inside element, there will have some error compared to the numerical solution. So anyway, so we can define those kind of residual first. So yeah, although we do not understanding exactly what is the Galadkin method, however, we are going to add this weight function or arbitrary value function in here, and then we are going to multiply our error and then sum the whole domain. Yeah, we hope that this become the zero, so that yeah, this is a Galadkin residual method itself. Yeah, you don't need to worry about the meaning of the Galadkin residual method. Yeah, actually, yeah, this part more easily understanding the meaning of this. Actually, that error, yeah, we always hope that this become the zero. However, yeah, it is hard to say that yeah, this cannot become the zero whole domain. Yeah, it's except special cases, so that they will have some infinity small value. So we hope that yeah, we want to minimize this summation of the error. So however, yeah, minimize or minimum, those kind of operator, yeah, it is hard to make exact equation. I mean that equal to zero, so that yeah, it's not uncomparable to using those kind of equation. However, using those kind of some arbitrary value, the summation always equal to zero. That means that this residual error will be reduced or minimized, so we can use the residual error itself, and then we are going to apply some arbitrary value in here. So yeah, and then this W weight function is arbitrary value. However, we are going to use this arbitrary value is interpolation or shape function of function. Yeah, first you cannot understand the meaning of this. Yeah, however, yeah, we are going to use some arbitrary value in here, but this value is firstly approximated value function, and then yeah, similarly, yeah, we also define the first order polynomial equation for the displacement variable. Yeah, finally this is become those kind of relationship u1 and u2, and then in here we changing this function as n1 and n2 as shape function. And similarly, we can say that this v variable also will have those kind of relationship, so that we are going to use this value in here. So yeah, in the textbook, so that they use different arbitrary value in here, yeah, compared to in my cases we can derive the two equation, yeah, we can handle the two equation in the directly, but yeah, in the textbook they use two different shape function. However, those kind of way we can obtain the solution by directly. So let's try this Galerkin residual method. So yeah, this is a exact cases, yeah, that will become 0. However, our solution is a numerical error. So yeah, the numerical residual maybe sorry, you had equal to, yeah, this is a residual error, so that this part always equal to 0. It is because that exact always equal to 0. We use those kind of equations, so that residual can be only, this is a residual only, and then this is arbitrary, but we are using those kind of some variable, arbitrary variable, yeah. So anyway, so yeah, and then yeah, this equation is a second order difference equation, but this u is a approximated solution, or n1 and n2, yeah, n1 u1, n2 u2, n1 and n2 is a function of the x. So yeah, this part always equal to 0, so that however, yeah, to handle this equation by first of the polynomial equation, we applied integration by part, so that this part equal to 0, this part itself, and then this part integrated the first time, and then this part, yeah, integrated this part again, and then this part derivative in this time, so that this is a integration by part, yeah, in Korea 부분적분. So that we obtained those kind of equation in here. So and then we are going to add this equation. I use some Einstein notation, but please do not confusing. Yeah, this is this means that this some matrix multiplication. This also this equation also, and then yeah, derivative means that, yeah, this means that, yeah, only this part derived. This u1 and u2 is some numerical solution. It's not a function, not the function of the x, so that only become, yeah, this become a b1 and b2. So anyway, so you can apply this part in here. So yeah, but please be careful that, yeah, the values are equal, yeah, but this part is some, yeah, this is a integration, but this part is remains different equation itself, so that we move to this part to the right hand side, and then yeah, here, yeah, vx and dv dx, yeah, dv dx means that, yeah, dv v1 b1 and b2, and then v1 and v2, and then multiplication, yeah, this also b1 and b2, u1 and u2, and then remaining ae, and then integration by x, and then remaining part is yeah, in here you just apply the this 0 equal to into the x variable in here. So and then, but yeah, let's think about, yeah, here, yeah, this part must be equal to 0. That means that this is a scalar value. However, due to the 1 by 2 and 2 by 1, and then 1 by 2 and 2 by 1. So yeah, you don't need to worry about the matrix transformations. So that anyway, so yeah, in here, so yeah, B1 and B2 is B1 is a minus 1 over L, B2 is a 1 over L, and then U2 and U1. And here I use a different notation, but to multiply these two equations, can you multiply this one? So we should take some transposes in here, but this value, this is some scalar value. So however, after the transpose, so that you can obtain the same value v. So then after transpose means that we are going to changing this b1 and this b2 and v1 and v2, and then integration ae. Okay. So in here, so after the v, let's go to the outside v1 v2. It is because that v1 and v2 is a independent variable by x, so that you don't need to worry about the integration of this part. Also, u1 and u2 is an independent variable. So u1 and u2. Here. So what is the b1? I say that this is this, and then these same vectors, but the transposes. So and here, the result, 2 by 1, 1 by 2, multiplication is a 2 by 2 matrices. So and then in here, so after the matrix, let's try to do matrix multiplication. So we can collect 1 over L square, and then the multiplication 1, different sign, -1 and -1 and 1. Looks like this, and then dx and u1, u2, and then but the integration ae and with the v1 and v2. Here. That result, and then but unfortunately there are no x variable in here. You can easily integrate it. And I mean that v1 and v2 and then L square 1. There are no function or value in here. This integration become the x from 0 to L, and then the value is equal to L, and then but you can cancel out this part in this part, and then the remaining things, and looks like this. We obtain the left hand side, and then let's check the right hand side also. In previous slide, we skip the details. Maybe right. And here, v is actually we can use n1 and n2 and v1 and v2, those kind of function, and u also you can use the same function formulation. But this u is derived by x, that become a b1 and b2 and u1 and u2. And here, this part looks like this, and here, and this part, and then for the matrix multiplication, we use a transposed variable. It is because that v and transposed v is always equal. It is because that this is a scalar values. But we use some matrix form. So that transposed vector can be v1 and v2 and n1 and n2. So v1 and v2, and n1 is a 1 minus x over L, and the n2 is a x over L. This is a correct form. And then please let's check the, yeah, there are some x variable in here, so that please add it here, and then minus, and then please add it in here. So after then we obtain those kind of value in here, but yeah, please don't forget the v1 and v2. So yeah, I don't have enough spaces, but the right hand side is equal to the AE v1 and v2 vector, and 1 minus, yeah, so they do not perform this one. Yeah, let's here, yeah, after the applying L, yeah, this big part equal to 0, and then this part is equal to 1, and then, yeah, how can I say that? Yeah, 0, 1 over L, 1 over L. Am I right? Yeah, and then minus, and then this time and this part, and then looks like this, and then yeah, so but just do not forget AE v1 and v2, and then this part become the sum. Anyway, we obtained some result. So, and then next time I will introduce more detail. And then, yeah, here, yeah, cross-section area and Young's modulus, and then this is a length, and then this part is just matrix with constant, and then u1 and u2 is an unknown variable. We are going to obtain the u1 and u2 value in here. So, and then, yeah, this part will be, yeah, some exact, yeah, we just say that we already known, yeah, this part known. However, yeah, v1 and v2, yeah, we say that this is also some nodal value in the arbitrary value, but yeah, in the both sides, they containing the same term at that time. Yeah, to match this equation, that means that, yeah, this v1 and v2 is an arbitrary value. So that, yeah, although v1 and v2 arbitrary value, we can make this equal condition by what? Yeah, remaining part must be equal. Yeah, so finally, yeah, remaining part, yeah, let's check about, yeah, AE over L, and then 2 by 2 matrices, and u1 and u2, and then, yeah, right hand side, yeah, I do not conclude the detail. This part is equal to the forces vectors. So yeah, next time I will show you the more good form. So anyway, those kind of equation, yeah, actually, yeah, in this time, yeah, v1 and v2 does not affected or included this equation. So anyway, we finally reached our same form of the FEM equation. So this is another method to obtain the Galatkin residual method. And then, yeah, I think that you can easily understanding the left hand side, although, yeah, I skipped the right hand side. However, yeah, in the previous slide, yeah, integration by part. Yeah, using the integration by part, yeah, this is some domain equation. Yeah, after we are going to cancel out this v value, so that you don't need to worry about it. So anyway, yeah, this equation always equal to 0. And then, however, this is not does not anymore. Yeah, this part is not the integration equation. Yeah, this is part some value in here. Yeah, this part is some function. Yeah, function of the x or function of the u, and then after L minus after x equal to 0. Yeah, this is just some become a specific value. Yeah, and then let's think about what is this value a and e and Young's modulus, and then say that this is this part, and then what is this Young's modulus and strain. This is a stress, and then what is this? Okay, this is a force. Stress and cross-section multiplication is a forces. So that forces at point L and forces at point 0. So next slide, I'm going to show you detail. First is a point L, means that maybe this is x equal to 0. This is equal to L. Maybe this part, it means that first nodal forces. This part become a second nodal forces, so that you don't worry about the right hand side. So anyway, so that using the integration by part, we can defining the surfaces or some nodal forces looks like this. So that this is a Galerkin residual method. So, and then in here, we use a 1D truss example, but generally, actually, this Young's modulus actually positioned in the middle of side, and this cross-section area actually is already integrated whole volume domain, so that we can changing the matrix forms again. So then, and then this is actually derived shape function. I means that this is a derivative of the shape function in the previous slide. So that this also derivative function. We can say that this is a B1 and B2 or B vectors or sometimes B matrices. So that we can changing this part B, and then this is a transposed B matrices. So that here this is a general stiffness matrices. This D is a Young's modulus or stiffness matrices depending on your system. So and then B is a derivative of the shape function. I don't think you are familiar with the shape function yet, but if you are familiar with shape function for our FEM system, you can just add the derivative shape function in these matrices. You can easily obtain the general stiffness matrix, actually local. This is another way to the Galerkin residual method. This method is you can apply any types of the different equation. That means that although in our lecture we only handle the solid mechanics, but heat transfer or fluid dynamics also can be described by the difference equation. So using the Galerkin residual method, you can just add some arbitrary wave function in front of your partial difference equation. You can derive your FEM equation. So after obtaining those kind of global local stiffness matrices, you can and then do the assembly process, and then after applying some boundary condition, you can obtain the solution. This is a way to use a Galerkin residual method for the FEM simulation.